Hello, my name is Jeff Messier. I'm a professor of electrical and computer engineering in the Schulich School of Engineering, and this is module one of my video lecture series on ENEL 343 at the University of Calgary. And for those of you who are not University of Calgary students, if you're just watching this video series, this is basically the second electronics class in sort of a typical electrical engineering kind of course stream. So this lecture series assumes that you've taken a basic kind of first year or freshman circuits class, and this course is going to build on it basically. And so this module is module number one, where we're going to be reviewing some, basically reviewing some basic concepts around what voltage and current and power are. And just a few words on how to watch these videos before we get started. So if this is the first time that you are doing a video lecture series or a course that uses video lectures, a couple important things to remember is that one of the nice things about video lectures is that you have full control over your listening and viewing experience. So if I'm going through stuff that you're already familiar with, feel free to fast forward or play at a higher speed to zip through it if it's all familiar. By the same token, if I'm going through something that's not familiar, it's fairly complicated, you need a chance to think about it, feel free to pause the video and think about it, rewind, listen to it again. And in that way you can have more of a customized or personalized learning experience. Also, I will be, as you can see here, using sort of an old school kind of paper and pencil kind of approach to these video lectures. I'll be talking and drawing diagrams on this pad of paper. You might want to take additional notes because I will be sort of speaking as I'm drawing the diagrams. And so some of the things that you need to remember for this course, I will just say, I won't necessarily write on the piece of paper. So make sure, while you're taking notes, you're jotting down some notes on what I'm saying in addition to just kind of the diagrams and stuff that I'm putting on the paper. So if that all sounds good, we're ready to get started. Okay, so let's start off by talking about some fundamental concepts. And again, this will be a bit of a review. And let's start with electric current. So electric current is basically just the rate of flow of electric charge. And the units of current are amperes or amps. And an amp is just a coulomb per second, right? So a coulomb is a measure of electric charge, and an amp is just how much charge we're transferring basically per unit time. And typically when we're representing current, we represent it as a flow that has a certain direction. And by convention, sort of the direction of positive current flow is the flow of positive charge. So if we think of current as kind of the flow of electrons, which is actually what it is, the direction of positive current flow is actually opposite to the direction of flow of the electrons. And just as kind of notation, we typically draw current as going through some kind of element, and this element could be a resistor, a capacitor, it could be a voltage source or a current source. And sometimes in our circuit, we label the nodes, which are basically sort of where the wires connect, using either numbers or letters. So in this case, I've labeled this end of the wire or this node as A, and this node as B. And if I were to draw the direction of current through this element using this arrow, I would represent that as a little lowercase I. Usually I use lowercase letters to represent voltage and current. And so if the current is going in this direction, a downward direction, I would say that this is current AB because it's going from node A to node B. And if we wanted to represent current going the opposite direction, I would write this as IBA. And of course, we can see that IAB is just the negative of IBA, right? And this negative sign just indicates that these two currents are going in the opposite direction. Sometimes you will see me represent current also as a function of time. So I'll write it as I as a function of time. And this is usually when we're dealing with things like sinusoids, where the value of the current varies as a function of time. Okay, the next concept is voltage. And the definition for voltage is the energy transferred per unit charge when charge moves across an element. And so I'll write that down and then I'll talk a little bit about what this actually means. So typically we think of voltage as kind of the push that pushes electric charge through a circuit and basically creates current, right? And so the whole point of working with electric circuits is to create current that flows through elements, and as the current flows through these elements, it delivers energy to those elements, and it does a job for us, basically, when it delivers this this energy. And so we can think of voltage, when we create a voltage, we're basically using some energy to gather up some charge that's ready to flow through our circuit. And so that's kind of where this concept of sort of a push for the electric charge through the circuit comes from. So that's, maybe not super precise, but it is kind of a useful analogy, and it does let us sort of understand what's going on. Typically, we give voltage a polarity across an element, and we can have a voltage polarity across either a source, which delivers energy to the circuit, or an element like a resistor or a capacitor or an inductor that dissipates energy. And so if I draw, again, just sort of our very generic circuit element here, and I label these ends of the two wires as A and B, if I represent the polarity of the voltage like this, I would say this is voltage AB. And if I represent the voltage like this, I would say that this is voltage BA. So basically the first letter in our subscript is just wherever the plus is located. And the units of voltage are volts, which is a joule per coulomb of charge, right? And so a joule is a unit of energy, and so we can think of, so 1 volt is basically how much energy we are going to either dissipate or deliver to a circuit per coulomb of charge, right? So again, you can think of it as a push or sort of gathering a bunch of energy and storing it in electric charge and getting it ready to do some work for us. So I want to talk a little bit more about this relationship between voltage, current, and energy. So all practical electric circuits have some sort of source, either a voltage or a current source, that supplies the circuit with an electric current, and that current carries energy. And then basically, as the current flows through the circuit, we use that energy to do some kind of useful job for us. And so one example, and this is an example that we'll be working with in this class, is let's say we have a voltage source. This voltage varies as a function of time. And so this is how we would draw our source. And we connect our voltage source to, let's say, a speaker. And then we ground our circuit. And so this voltage source would create an electric current that we would represent as I of t. I'm showing these as a function of time because for this particular example, let's assume that the voltage and the resulting current are varying as a function of time. And so the voltage source creates a current or gathers a bunch of charge together, gives that charge some energy. That charge then flows in the form of current down our wire into, in this case, a speaker. And then what happens when the current flows through the speaker is that it delivers this energy to the speaker. The speaker then translates the energy of the current into actual mechanical motion to vibrate some sort of speaker diaphragm. And then that creates sort of ripples of air pressure that we can perceive with our ears as sound. So that's an example of one sort of circuit that takes, the energy of electric current and then uses it to do an actual job for us. So let's think a little bit more closely about what a source is doing. So I'm going to draw another voltage source, and this time I'm going to draw a DC source or a battery. So this is the symbol for a battery. And the positive polarity of the battery is at the top. The negative polarity is at the bottom. Now we can think of the battery as using chemical energy to collect a bunch of positive charges at its positive polarity that have a certain amount of energy and are ready to do work as soon as we close our switch. As soon as we connect our battery to some kind of circuit and close our switch. As soon as we close our switch, these positive charges are going to rush through our wire into our circuit and do some work. And so we would represent current flow in this particular case as moving in this direction. And so you can think of these, positively charged particles running through our circuit, coming back, and then, moving from the from the negative polarity back up to the positive polarity, getting recharged with energy, and then flowing back around and doing more work. So basically, whenever we have current flow like this, and whenever current flows from the negative polarity of an element to the positive polarity of the element, we understand this element, in this case a voltage source, as doing some work, adding some energy to the circuit in order to, give some energy to these positively charged particles so we can make use of it in our circuit. So whenever current flows from negative to positive, it's because we have an element that is doing some work and adding some energy to the circuit. And this is, in the case of a battery, it's converting chemical energy to electrical energy. In the case of a generator, where you're cranking something with using a turbine, it's converting mechanical energy into electrical energy. And now let's think about what happens when current flows through a resistor. So this is how we draw a resistor R. Whoops, R. And when current flows into a resistor in this direction, there's a voltage drop across the resistor that looks like that. And we'll just represent this voltage drop as V. Now note that the voltage polarity is opposite across the resistor when we compare it to our source. So when current flows through a resistor, it flows into the positive terminal and it exits from the negative terminal. And that's opposite to the source. When current flows through a source, it enters through the negative terminal and exits through the positive terminal. That's because the resistor, rather than adding energy to the circuit, is taking it out of the circuit. So whenever current flows through an element that dissipates energy, it creates a voltage drop across the element where the positive part is at the point of entry of the current. And in this case, a resistor takes energy out of the circuit by converting electrical energy into heat. And sometimes that's what we want. Like if we're designing an electric heater of some sort, this is exactly what we want. However, often it's not what we want. So for example, when energy flows through the elements of a computer chip, even though we try to minimize resistance in digital circuits, there always is a certain amount of resistance. And that causes the computer chips to heat up. And in many cases, it's getting rid of that waste heat that sort of limits the speed of the computer chips. And it also is a big part of the environmental impact of large computing or cloud computing farms. Okay, so moving on from energy, now we can talk a little bit about power. And power is the rate of energy transfer per unit time, or said another way, how much work is done per unit time. And the units of power is watts. And a watt is just equal to a joule per second. So how much energy is how many joules of energy are transferred in a second? And in an electrical circuit, we can think of power being generated or absorbed. An element that adds energy to our circuit is generating power. An element that dissipates energy from our circuit or removes energy from the circuit is absorbing power. And so by convention, if we have an element that absorbs power, we think of that power as being positive. And so the classic example of an element that absorbs energy is the resistor. So when current flows through the resistor, as we saw just now, it creates a voltage drop across the resistor. And the positive polarity of the voltage drop is at the terminal where the current enters the resistor. And the formula for dissipated power or absorbed power, P, is just voltage times current. And, whenever you're working with formulas, it's always kind of useful to do a unit check to make sure that your units work out. And so we know that the units of voltage are volts, and a volt is a joule per coulomb. We know that amps are coulombs per second. And so the coulombs cancel, and we're left with joules per second which of course is the unit of watts. So we know that our formula is correct. Now, if we want to look at a generating element rather than an absorbing element, we draw this maybe as a circle, which is sort of the way that we represent a voltage source. So the positive terminal is here, negative is here, the voltage value is V. When we're dealing with a source, the current flows in this direction, right? It flows in the opposite direction because we're adding energy to the circuit. We're basically sort of gathering up positively charged elements and placing them at our positive terminal, ready to flow through the circuit and do some work for us. And the formula for power for a generating element is exactly the same. It's voltage times current, except we just put a negative sign in front of it to represent the fact that we're generating rather than absorbing power. And so, as I said earlier, when we absorb power, we always sort of get something for the energy that gets absorbed. So when the energy is removed from our current, something always happens. Maybe we get some mechanical motion in our speaker. Maybe we get some heat generated. And sometimes it's what we want if we're, like I said, doing sort of an electric heater type design. But sometimes the energy is dissipated in a way that we don't want. So for example, waste heat in a digital circuit. And since Ohm's law tells us that voltage is equal to current times resistance, we can actually express our power formula in a couple of different ways. So P is equal to current times voltage. And if we substitute in Ohm's law, we know that current is equal to voltage divided by resistance times voltage. So the power dissipated by a resistor, for example, or absorbed by a resistor, is equal to the square of the voltage drop across that resistor divided by the resistance value. And we can put this in another form. Power is equal to current times voltage. We know that voltage is equal to current times resistance, again using Ohm's law. And so the power dissipated by a resistor or absorbed by a resistor is equal to the square of the current times the resistance. So just two different other formulas for power that can come in handy. So kind of continuing on with this theme of adding energy to a circuit, I would like to say a few words about voltage and current sources. In particular, independent voltage and current sources. So first of all, just a couple of definitions. An active element is an element that generates energy for the circuit or adds energy to our circuit. And this means that both voltage and current sources are active elements. And so when we draw a voltage source, typically in this class I'll be drawing them as circles, and I'll give a little bit of a polarity, or I will indicate the polarity of the voltage source. One terminal will be the positive terminal, the other one will be the negative terminal. Sometimes I'll put the polarity inside the circle, sometimes I'll put it beside the circle. So this is a voltage source, and when I represent a current source, we won't deal with current sources as commonly in this class, but if I do represent a current source, then I'll draw a circle with a little arrow, and that arrow indicates the direction of the flow of current. And both voltage and current sources add energy to a circuit, so they are considered active elements. And when we say that they're independent sources, that means that an independent voltage or current source maintains its voltage or current no matter what else is happening in the circuit. So no matter what else is going on, an ideal independent voltage source will always maintain its voltage, and an ideal independent current source will always maintain its current. So an example, an example of a typical voltage source, I guess the classic example is a battery. So a battery is an independent voltage source. Also, we often model generators as independent voltage sources as well. And those are, two very common circuit elements that you see. Independent current sources are a little bit more rare. They have to actually be, or they're typically built using transistors. So you can design a transistor circuit that will behave as a constant current source. And probably these days the most common application of current sources are for LED lights. So any of the LED light bulbs that you're using right now are powered using constant current source circuits. So we talk about ideal voltage and current sources, and I just want to finish up by talking a little bit about what a non-ideal voltage and current source looks like. And so a non-ideal voltage source can't apply its full voltage across a circuit because it has a little bit of an internal resistance. So And so basically we model a non-ideal voltage source as an ideal voltage source that has some voltage V in addition to some internal resistance in series with the voltage source. And then, I'll draw a little box around this whole thing. And so the circuit inside the box basically represents our non-ideal or our practical voltage source. And so we have an ideal voltage source inside, and then some internal resistance that reduces the amount of voltage that we can apply across our circuit, so we don't quite get our full V applied across our circuit because there is a bit of a voltage drop across this internal resistance. And in addition, this internal resistance serves to absorb energy and kind of dissipate a little bit of the energy of our ideal voltage source. And it represents the waste or inefficiency of our voltage source. For example, maybe the internal resistances of the windings in our generator, or perhaps some inefficiency in the chemical process of our battery, basically. And I guess for perspective, some typical values for this internal resistance for, let's say, like a AA battery, for example, is 0.15 ohms, so 150 milliohms, so pretty small. Now, An ideal current source delivers the same current regardless of the resistance that it's driving, right? So I guess ideal current source would look like this. And we've got some R load, or maybe I'll just call this RL. And so we've got some current being produced by our current source I, and it doesn't matter what RL is, I is always constant. So you can imagine basically the more we increase our current, the kind of harder the ideal current source has to work, right? Because it has to push harder to get the that same amount of current through that resistance. In practice, a non-ideal sort of practical current source does have an increasing amount of trouble supplying a constant current as we increase the resistance of our load. And we basically model that using an internal resistance again, but one that is in parallel with our ideal current source. So, non-ideal current source. Looks like this, where we've got our ideal current source. And in parallel, we have some internal resistance. And then we just put a box around this. So everything inside the dotted box would be our non-ideal current source. And then we still kind of drive our same load resistance and make sure everything here is grounded. So now, if the load resistance is small compared to this internal resistance, then if we calculate sort of the equivalent resistance in parallel, it's going to basically be equal to the load resistance, and that means most of the current is going to be flowing through our load resistance. But as we increase our load resistance, more and more of the current starts to get shunted off through our internal resistance, and that represents kind of inefficiency or waste. And it's a little harder to find sort of typical values for the internal resistance for current source. It sort of depends on the transistor circuit design that you're using to create your current source. But, reasonable values tend to be in the mega ohm range, basically.